So here we will discuss the pre-M phases and D-M phases circuits and how do they work for the in during the transmission of a frequency modulated or a phase modulated signal. So in one of the previous videos, we have seen these expressions for the interference output YD for PM and for FM signal. So it can be observed from these expressions that the if the carrier amplitude A, if this is high, the interference effect is small. The overall expression is small because the amplitude appears in the denominator. So this behavior is very different from AM signals because the interference is independent of the carrier amplitude in case of AM. So hence angle modulated systems are much better than AM systems at suppressing weak interference. So if the interference I is weak in AM or in PM or FM signals, we can reduce or suppress it by using a high value of the carrier amplitude A. So that is why, because of this flexibility that AM or that PM or FM systems give us, they are generally used instead of the AM signals. So if we plot those expressions here, so we can see as the frequency increases, the amount of interference is shown on the y-axis, on the vertical axis. So we can see that for FM, with the increase in frequency, the amount of interference increases. Because for FM, this is the relation for the amplitude. So this omega, as this increases, the interference amplitude increases. And for PM, the interference output remains constant because PM, the intensity of the interference output is dependent upon I by A. So it's independent of the frequency. So here we can see from this plot an interesting phenomena that for the lower frequencies, the interference in the FM signal is low, and for higher frequencies the interference in the PM signal is low. So let's design a circuit. So what PM phases and pre-M phases and DM phases do is they allow us to design a circuit that uses FM behavior in the low frequency region and the PM behavior in the high frequency region. So our aim in this would be to get a signal, to get a response like this, a response of interference which is shown by the solid black line. So this is the FM with pre-M phases and DM phases. So this is our aim. So let's see how we achieve this aim. So as we saw that the noise power in the receiver output is concentrated at high frequencies. So this is clear to us from what we saw in the previous discussion. The power spectral density of an audio signal MT, let's say this is the audio signal we are going to transmit, it's generally concentrated in the low frequency region. It's below 2.1 kilohertz. So the noise PSD is concentrated at high frequencies where MT is weakest. So this is what we observed from the previous plots. So this situation helps in reducing the noise significantly by using the pre-M phases and DM phases blocks in the FM system. So what we do is, at the transmitter, the weaker high frequency components beyond 2.1 kilohertz of the audio signal are boosted before modulation. So this process is called pre-M phases, and we use a filter to do this. It's called pre-M phases filter. It has a, let's say, a transfer function of HPF. So I repeat, so at the transmitter, the frequencies of the signal, audio signal, that are higher than 2.1 kilohertz, those frequency components are boosted by using a pre-M phases filter, right, which is denoted by this transfer function HPF. So the block diagram of this system is shown here. This is our signal input audio signal MT. This is the pre-M phases circuit, the block, and after that we have the frequency modulator. So the signal is transmitted, we have a frequency demodulator, and then we have a DM phases block here, and at the output we get our signal MT, which is amplified by an amount of K. So what happens at the receiver? The demodulator output is passed through this demodulator output is passed through a DM phases circuit. What it does is it has an exactly opposite response to the pre-M phases circuit. So that means the DM phases filter undergoes pre-M phases by attenuating or de-emphasizing the high frequency components, which is exactly the opposite of what was done at the transmitter. So it de-emphasizes or attenuates the high frequency components beyond 2.1 kilohertz, and so this restores the original signal MT. So now, how does it benefit? How does it reduce the noise or interference? So remember, noise enters at the channel. So noise enters at this point. So this pre-emphasis has been done before the noise enters, and de-emphasis is done after the noise enters. So when we de-emphasize, when we reduce, attenuate the high frequency components, we effectively bring the signal back empty, to the value of MT, and what another effect that we get is the noise is further reduced. It's also de-emphasized along with the signal that is received after the demodulator. So noise is not pre-emphasized because pre-emphasis is before the noise enters, but it has been de-emphasized, so that's why the overall noise is reduced in the circuit, in this complete transmission system. So noise passes through the DM phases filter, which attenuates its higher frequency components where most of the noise power is concentrated. So the process of pre-M phases and DM phases, which is generally called PDE, leaves the desired signal untouched but reduces the noise power considerably. So that's why it's a very important step or very important process in the PM or FM signal transmission. So this is achieved by generally combining the FM and PM. So now we'll look into the practical circuits that are used to achieve this goal. So for FM has smaller interference than PM at low frequencies, while the opposite is true at high frequencies. So this has been observed until now. So if we can make our system behave like FM at lower frequencies and behave like PM at high frequencies, we will have best of the both worlds. So we can take benefit of the features of FM at low frequencies and the desirable features of PM at high frequencies. So this is accomplished in commercial systems by using the pre-M phases before modulation and DM phases after modulation. We use these filters HPF and HDF, which has been discussed until now. So now what are the practical circuits that are used? So this circuit is a commonly used pre-M phases circuit. What it has is it has a resistor initially in parallel with a capacitor at the input. After that it's followed by another resistor. So the transfer function of this circuit looks like this. So the frequency F1, which is here, which is around 2.1 kilohertz, and F2 is typically, this one is 30 kilohertz or more, well beyond, and this 30 kilohertz is well beyond the audio range. So these filters can be realized by simple RC circuits, as you can see here. The choice of F1, that is 2.1 kilohertz, is purely an experimental choice. So through experiments it has been observed that this gives the best results. So if we quickly look at the circuit for low frequency of MT, most of the current this capacitor almost acts as an open circuit. So most of the current passes through this R1 that we have here, right? So the output response, the transfer function, which is the output divided by this input, is almost a straight line in that case. So as the frequency of this signal increases, the input signal frequency increases, this most of the current starts flowing through the capacitor, right? So that means the capacitor is bypassing the resistor generally. So most of the voltage output now appears at this resistor, because this resistor is being in a way ignored, and so this acts as a very low resistance value. So most of the voltage appears at this resistor. So the output at this point increases slowly with the frequency. So that's why we have a straight line, right? So this is how this transfer function can be explained with the help of the circuit. Now it was found that this choice of f1, that is 2.1 kilohertz, maintained the same peak amplitude MP with or without preamp phases. So we want to keep this amplitude MP for our signal, audio signal, almost the same. So that's why it was observed experimentally, but that by using 2.1 kilohertz we get the best performance. So this satisfied the constraint of a fixed transmission bandwidth. So since the bandwidth in FM and PM is dependent upon the amplitude of the audio signal or the message signal, so if this amplitude remains constant, the bandwidth, required bandwidth, will remain constant. Now the transfer function of the preamp phases filter that we saw in the previous slide is given by this expression. So we have 2 pi f. F is the frequency at any time. Omega 1 is the first cutoff frequency, that is f is equal to 2.1 kilohertz. Omega 2 is the point where, so omega 1 starts from here, and then omega 2 is over here, right? So k is the gain, and its value is equal to omega 2 by omega 1, which we have substituted here. Now the values of omega 1, because it was a resistor in parallel with a capacitor, that is equal to 1 over R1C. Then for the omega 2, it's the 1 over R equivalent, where R equivalent is the parallel combination of the two resistors that we had seen in the previous circuit. Now if we look at this transfer function, for values of 2 pi f, any frequency 2 pi f that are much less than omega 1, that is if we are located somewhere here, then this transfer function almost gives us a straight line. It's almost equal to 1, right? So that's why we get a straight line in the plot that we had seen here. Similarly, if we look at the values of 2 pi f that are greater, much greater than omega 1, but they are much smaller than omega 2, the transfer function has this sort of shape, right? This the transfer function is reduced to this expression. So if we look at this expression, the output or the transfer function increases with respect to frequency. So that's why we get a straight line for this region. So thus the pre-emphasizer acts as a differentiator. So when we have a straight line, we know that this is like so if we have a straight line transfer function, that is the transfer function for a differentiator. Now if you remember, for the PM, for phase modulation, we use the differential of the message signal to modulate the frequency, right? So in FM, the frequency modulation is dependent upon the amplitude of the message signal. In PM, the modulation frequency is dependent upon the phase dependent upon the amplitude of the differential of MT, the message signal. So that's why in this region if we are having a differentiation, so that means we are effectively applying phase modulation, right? So this means that FM with preamp phases, DM phases, is FM over the modulating signal frequency range. So between this range, since we have a straight line, so we are applying FM. Beyond this range, since we have a differentiation of the modulating signal that is between 2.1 to 15 kilohertz, we are applying PM. So effectively we are having the best of the both worlds. So this is what happens at the preamp phases. Now the DM phases circuit is generally more simpler. So we have a resistor in series with a capacitor. The transfer function would be this output divided by the input. As you can see here, this is the DM phases circuit's transfer function, which is omega 1 divided by j 2 pi f plus omega 1, where omega 1 is the 1 over the cutoff frequency and given by 1 over RC. Now if we plot the transfer function it looks like this. For lower frequencies up to omega 1, it's a straight line, and for higher frequencies it's an it's a straight line decreasing. Just it's exactly the opposite of what we had for the pre-M phases. So for pre-M phases we had a straight line that was increasing in amplitude. For DM phases we have a straight line with a negative slope and almost the same rate of decrease as the rate of increase at the pre-M phases. So this is almost like a low pass filter, and if we combine these two, we will get the signal back at the output. So the combined effect, that is the multiplication of the pre-M phases and DM phases, is almost equal to 1. How is that true? Because if you look at 2 pi f, if at any frequency 2 pi f is much less than omega 2, we will see that the pre-M phases circuit in this region has this expression. So if this expression is exactly the opposite, 1 over HD, it's the reciprocal of the DM phases circuit. So when we multiply these two, we get a value of equal to 1. So overall the transfer function of the system is equal to 1. So the message signal remains the same. However, we have achieved more compression or suppression of the noise through this mechanism. So over a baseband of 0 to 15 kilohertz, which covers all the audio signal, the response of the complete transfer function, which is the product of the two transfer functions, is equal to 1. So benefit of pre-M phases and DM phases is improvement in the interference characteristics, because the interference from unwanted signals and the neighboring stations enters after the transmitter stage. It undergoes only DM phases operations, right? So not the boosting or pre-M phases. Hence, interference amplitudes for frequencies beyond 2.1 kilohertz undergo attenuation and is roughly linear with frequency, right? So this is the complete discussion about the pre-M phases or DM phases circuit. If you have any questions, you can ask in the comments section. Thank you.